In this video, I want to show you how the convolution by using Fourier transforms can be very helpful in calculating path integrals. In particular, in quantum mechanics, the path integral formulation provides a way to calculate quantum amplitudes for a particle to move from point x at t equal to 0 to point y at t equal to capital T. So let's say this is point y at t equal to capital T. We start at x at t equal to 0. So we have some kind of evolution from this state to this state here. The amplitude is given by summing over all the possible paths or trajectories connecting these 2 points. Each path contributes a phase factor determined by the classical action associated with the path. So it's easier to write down than to explain in words. Let's start from a certain action that we call S, and we consider a free particle, and for simplicity we set the mass of the particle to 1 and the reduced Planck constant h bar equal to 1 so that our action simplifies. In particular, the action is the integral over dt of the Lagrangian. The Lagrangian in this case is simply x dot squared over 2. So the mass of the particle is 1, therefore we only have x dot squared over 2. In general, this would be simply multiplied by m, but in this way we can avoid writing down m all the time. We write down the action. And then we have the exponential of the kind e to the I s over h bar, but since we have set h bar equal to 1, we can simply write e to the is, which is a functional because it depends on x dot. So we can write it like this as a functional. And then, if we want to obtain the amplitude to evaluate the evolution from the point x to the point y, we have to integrate this exponential over x, and the measure is quite complicated in path integrals because this is proportional to an infinite amount of differentials, basically dx at some time t1, dx at some time t2, ... And basically, if we consider the following interval from 0 to capital T, so this is the interval which helps describe the motion of time, so the passing of time. And we will discretize this to evaluate the path integral. This is usually what is done. So we discretize the time interval in this case because the variable that we are integrating over is a function, the function x, which depends on time. So we are integrating over a function that depends on time. So this time interval is important because it helps us describe how the function varies, and therefore it helps us keep track of all these differentials. So this is the idea. I know it's it might sound difficult to follow at first, but anyway, I will explain how we can do this calculation for this specific case, and we'll see that it will lead us to the Schrödinger equation. So we have to integrate over all these differentials, and in particular we have to start at x of 0, which we define to be x, and x of capital T, which we define to be y. So the final displacement is y, whereas the initial displacement is x. The way to think about this, if I draw this graph, and here we have the interval 0, capital T, at 0 we have some displacement x of 0, which is equal to x, we define it to be x, and at t equal to capital T we have some displacement x of t, which is also equal to y, as I said earlier. The path integral focuses on all the possible trajectories that take me from this value to this, and all the possible paths, if you think about it, are infinitely many. So there is an infinite amount of them, but the path integral formulation of quantum mechanics tells me that some paths are more likely than others. Now, this amplitude here, we can call it k, and it is a function of x minus y, as we will see, and it also depends on the time interval, which has a length capital T. Now, in order to calculate this integral, which is quite complicated, the first thing that we are going to do is we are going to rewrite this exponential, I mean the argument of the exponential without the imaginary unit. And it is possible to do it in the following way. So we have I, the action is an integral over dt of the Lagrangian, and in our case the Lagrangian is x dot squared, so it's d squared x dt squared. Now we do the so-called Wick rotation, which allows us to rewrite the variable t, the variable of time, which is of course a real number. We write it as an imaginary number like this. So we go from t to I t. So I rewrite the same variable t, but this variable, this t here, represents an imaginary time because it is multiplied by I, and it has to create real time. So it's convenient because of the following reason. So we can rewrite this as integral. Now let's write it as dit d squared x dit squared. So if you check this, basically this ratio, it's like this, dt over dt squared, but you can see that I have added an additional unit of I in the denominator because we have I squared, if you check, and therefore this I will cancel this I. But you have to remember that we also have, we have to get I here, in this position, and since I have added a factor of I in the denominator, here I must have I squared, and therefore what we get is minus the integral, the same integral here. So basically what this means is that we can consider, instead of writing this integral here with the imaginary unit I can put a minus, and then instead of considering real time, I'm considering imaginary time, purely imaginary. So this time here, if we write the exponential like this, in this form, should be thought as a purely imaginary number, something like I times epsilon, where epsilon is a real quantity. Now, what's the purpose of this? The purpose of this is to evaluate the integral with by means of convergent integrals. So these integrals will become convergent, and after we do the calculations, at the end of the calculation, we can go back from imaginary time to real time by means of a simple substitution. So in here, the idea to evaluate the path integral is to divide the time interval from 0 to t into small slices of length epsilon. So we have a finite number of these slices, and let's imagine that the number of slices is equal to n, and therefore epsilon times n should be equal to capital T, and therefore the number of slices is t over epsilon. Simple as that. So as we let epsilon go to 0, of course we have an infinite amount of such slices. Now, at each time slice, the particle makes a small step, and the total path is built up from these infinitesimal steps. So the path integral can be approximated like this. We have an integral from x to y. Remember that x is x of 0 and y is x of t, like this. We have a product, an infinite product over the variable t of exponentials. So first let me write it down. X of minus 1/2 x of t plus epsilon minus x of t, and then we divide this by epsilon. This is squared, and then this is multiplied by epsilon, and we close the bracket here, and then we also have the integration measure dx like this. Now, this can also be written like this. We can simplify this epsilon with one of the epsilons in the denominator. So we have something like this, only the numerator is squared. And remember that epsilon represents the time slice, so it's basically some kind of differential of time, which is the small increment in the time variable. Now, let's analyze this exponential more carefully. That's important because it's a Gaussian factor. It's a Gaussian function which is centered at x of t, whose variance is equal to epsilon. Each factor corresponds to the probability amplitude for the particle to move a small distance in time, epsilon. The multiple integrals represent a series of Gaussian convolutions over adjacent time slices. So you can see here that we have a series of convolutions. Basically, we have an integral of functions which are very close to each other. This means that our amplitude k of x minus y t, and we really have to prove that indeed we get this difference, so the function depends on this difference here. But we have shown that the integral can be written as a series of convolutions. In particular, we call each Gaussian factor g sub epsilon. Epsilon is the variance of the Gaussian function. All the Gaussian functions have the same variance. They are only centered at different points, and this makes up the whole convolution. So we have g sub epsilon convolved with itself how many times? Well, n times, because it is the number of slices, which is t over epsilon. Now, when we move from the space domain to the Fourier domain, and by space domain in this case I mean from the space x minus y, from this variable to the variable p. Now it's important to highlight that we have to start from x minus y, because the reason is that we are taking these convolutions here, all these convolutions. When we have a convolution between two functions, for example, let's call them a and b, we have an integral of the kind a of x minus tau, b of tau, d tau, and you can see that this function, the convolution, depends only on x. So basically it's the sum of these two arguments. So we have x minus tau plus tau, which is equal to x. And by replicating this kind of reasoning here, what you're going to get x minus y. This is a property of convolutions. And once we take this transform, this is the important part, this convolution here in the Fourier domain will be replaced by multiplications. So these convolutions operators will be replaced by simple multiplications. So in particular, the transform k hat of p t, so I replaced x minus y with p, will be the transform of this. So we have g transform sub epsilon, which will depend on p, and then this is multiplied by itself n times. So we can simply write this raised to the power n, or t over epsilon, because n is equal to t over epsilon. But now, the Fourier transform of a Gaussian function is still a Gaussian function. This is the property of Fourier transforms and Gaussian functions. This will be another Gaussian function. In particular, the Gaussian function is of the form e to the minus p squared over 2 multiplied by the variance of the initial function. So we have epsilon here. And it appears in the numerator, whereas in the starting function, epsilon was in the denominator. So this is the property of Fourier transforms and Gaussian functions. In this case, this appears in the numerator. This can be done. If you take the Fourier transform of a Gaussian function, you can witness this property. You can derive this property. So basically, this will give us e to the minus p squared over 2 times t, like this. Now, if we go back to our initial domain, so we have k of x minus y t, we have to take the inverse transform of this, and basically we get some multiplicative factor here, because remember that we started from this path integral, so this dx is proportional to the product of differentials of the kind dx of t1, and in particular t1 was 0, so dx of 0, dx of 0 plus a small increment, which was epsilon, so x of epsilon. Then we have d of x of 2 epsilon, dot dot dot, and we have d of dx of n epsilon. This is the last increment, so the last differential, but there is a proportionality, so we can multiply this by any factor, and therefore this function is not really equal to this, but it's actually proportional to that. So here, to be more precise, I should put a proportionality constant, sorry, a proportionality symbol. And the inverse function, the inverse transform of that is e to the minus x minus y squared over 2, and this t will appear in the denominator because of what I said earlier. So this represents, in particular, this is the variance of this function. When we go to the Fourier domain, the variance appears in the numerator. Now, there is actually a way to derive also the proportionality factor here. How do we derive that? Well, we can impose the normalization condition of k, so in particular k of x minus y t can be thought of as the probability to find a particle evolving from the point x to the point y. But if we integrate the function over y, basically we are integrating over this argument. So it is the probability of finding the particle anywhere. So it is the probability of the particle taking any possible path. And of course, it makes sense to set this equal to 1 because we want the probabilities to normalize, to be normalized. So we can put this function in here and integrate. So we integrate from minus infinity to plus infinity, and you can find the factor that has to multiply this function in such a way that this function can be defined to be normalized, so that this integral gives 1. And once you do that, you can show that the function, this one, with the multiplicative factor that you can find from this condition, satisfies the following equation. So the derivative with respect to capital T of k of, let's call the argument x instead of x minus y. So you simply have to replace x minus y with x in here. So I can call this x, and therefore here I have to replace it with x. If I do that, x, and then here we have t, this is equal to del squared. So in particular, here we only have one spatial variable, so we can write the partial derivative with respect to x twice. So it's a second derivative multiplied by 1/2, and then we have k of x t. And if you want to go from imaginary time to, if you want to return to real time, because remember that we have made a simplification to do all the calculations, we assume that our time variable is actually an imaginary variable, a purely imaginary variable. So if we want to get back to real time, we have to replace t with it, where in this case t is real. And therefore, by doing that, you have d over dt, you have a factor of 1 over I that you can put on the right. Here you have k, and here you have I over 2 d squared dx squared k. If you multiply by minus I both sides, you can rewrite the equation like this. And this represents the Schrödinger equation for a free particle.